think that there's some more interesting things to state before we get to the halfway point. So that's starting with an abelian scheme. Let's see what happens if we instead start with an abelian variety over the fraction field. Alright, so this is a theorem, and it takes much of the BLR book to show this, which you can look at if you want, but then we don't have time in this seminar to show this. So we'll let AK be an abelian variety over K, over spec K. Variety over spec K, where K is the fraction field of the Dedekind scheme. Then AK admits a Neron model. Over R. So yes, sorry, in this case I'm working with, so S is S equals spec R for R, a Dedekind domain. Then it's an error model over spec R.
Why are you suddenly restricting to the affine case? Why not just take S as before? I mean, the thing is unique up to unique small physics, so it will glue on overlaps. And so if you know it for affines, then you know it for all Dedekind schemes.
That's right. Yeah, I'm only doing that because later I look at DVR so much. But yes, that's true. Let me reset this.
No, don't change it. It's fine.
Oh, okay.
What you've written is true, right? When you think.
Sure. Yeah. So I mean, this is the case of I mean, this is the affine case, but we can just take a Dedekind scheme if we want. This still works fine.
I'm not going to start listing everything that's true that God hasn't written on the board.
All right. So this is nice. Let me now introduce the concept of good reduction of the abelian variety. This will be very important for looking at Sertate in a bit. So I'll let S be a Dedekind scheme. Field of fractions K as before, and I'll let AK be an abelian variety. Then we say that AK has good reduction at a close point S. If AK extends to a smooth, proper scheme which I call, let's call it A bar over OSS. Yes. Okay, so this is it almost looks like a Neron model. This definition, and it turns out that if we have a Neron model that's proper over OSS, then this will be that'll imply that AK has good reduction at the close point S. Okay, so let's look at an example now before the break. Yes.
No,
Oh, sorry. So we'll look at elliptic curves. And as I mentioned, this is a particularly nice case because we can be very explicit with it. right, so example, elliptic curves. So in this, I'll assume that I'll be working over a strictly Henselian discrete valuation ring. So let's assume that R is a strictly Henselian DVR. Whose residue field has characteristic not 2 or 3. So the characteristics of K is not equal to 2 or 3. And I'll assume that we have some elliptic curve, EK over K is an elliptic curve defined over where it's in T2K, and it's just given by the Weierstrass form elliptic curve in T2K, given by its Weierstrass form. So y squared z equals x cubed plus beta xz squared plus y z cubed. All right, so I'm sure we've all seen this multiple times, and from this we get the discriminant.
Shouldn't be a y, right? That's a very weird elliptic curve.
I think it's a rectangle.
I guess technically, I mean, it's degree 3 if it's through this elliptic curve. I usually tell the pointers, but
Oh, that's true. It is gamma. Yes. So discriminant delta, which is given in terms of the coefficients, so it's 4 beta cubed plus 27 gamma squared, and the J invariant what we call J, so that's 2 to the 6 times 3 cubed times 4 beta cubed divided by delta. Okay, so this is an abelian variety, and without loss of generality, I'll assume that the unit section is given by the point 0, 1, 0. So assume without loss of generality, just after a change of coordinates, that 0, 1, 0 is the unit section. And furthermore, just to finish off the setup, I'll let pi be a uniformizer of R with evaluation V All right, so our goal here is to construct a Neron model of this elliptic curve over R. And it turns out that we can. I mean, this just follows by the existence theorem, but let's see how we do it explicitly. So for this, we need a quick lemma. And this is lemma 1.52 of BLR. All right, so given n in Z, the change of coordinates and if you know what this is, I'm just trying to find the minimal Weierstrass model. So the change of coordinates given by, so we send x, y, z to pi to the negative 2n. Remember, pi is the uniformizer, it's an element of k. Pi to the negative 3n, distribute x, y, z. This induces the change in the discriminant. So it sends our old discriminant to the new discriminant, which is just pi to the 12n delta. It sends our it has beta to 4 times pi to the 4n beta, and this sends gamma to pi to the 6n gamma. All right, so this is all very explicit. Once you've chosen all your, once you fixed pi and whatnot. All right, so the important point here is that after changing, or after using this change of coordinates with a suitable n, we can assume, first of all, that the beta and gamma lie in R. So our equation is defined over R. So from this, we can assume
Something's not right. If I think n is 0, where does the beta go to 4 beta come from? Sorry, I mean, I'm not saying it matters, I'm just observing something.
no, that's very true.
Thank you.
That is a bit
Perhaps n should not be 0. Perhaps I'm wrong.
Well, the 4 should be.
Perhaps the 4 should be also in the
I
power.
think I agree too. Yeah, because you're scaling the x by 9.
Yes, there's no 4. And so
Okay. Oh, there is a 4.
there's a 4. It's not there. Very good catch. That's true. Okay, so from this, we can assume that beta and gamma lie in R, and that we have minimality of the following. So the min of the valuation of beta cubed and the valuation of gamma squared is minimal with respect to all the values of n. And we call this the minimal Weierstrass equation, and it defines the minimal Weierstrass model of E. So this defines the minimal Weierstrass model E bar. This is defined over R because we've chosen the coordinates such that this holds. Over spec R of E K over K. All right. Now, the exciting part is that, so in good circumstances, good in quotations, this is actually, this defines the Neron model. So in good circumstances, this defines the Neron model. Of EK over K. Now, in general, this does not hold. But what we can do, sorry. So if we work a bit harder, then we can use a series of blowups to actually get the Neron model from this minimal Weierstrass model. This is so. I'm not going to go through this. There's just a bunch of cases that you need to work through, but it's given in PLR in section 1.5, and it's all very explicit. So, I mean, the takeaway from this example should be that the case, or at least when you're showing elliptic curves, Neron models are not some kind of abstract idea. They're very concrete, and you can calculate them very explicit. All right, so before we take a break, let me just say where we're going and why. So if you've read the list of topics, then you'll see that we're interested in something called the Picard scheme, which is a bit mystifying at first. But the reason for this, so this is kind of an aside as to where we're going. Right, so if we have a curve C over K, then we can consider the Jacobian of C. So we take the Jacobian of C. This is the set of all line bundles of degree 0 on C, and in the case of elliptic curves, so E is I mean, there's a very nice map from E to its Jacobian, so we can be very explicit in that case. But the point is, in general, if we take any curve, then the Jacobian is an abelian variety over K. So JC is an abelian variety. And then we can find its Neron model, which is very nice. Now, if instead we start with something that isn't a curve, we start with X, for example. So X is some higher dimensional variety, for example. Then it doesn't make sense to discuss the Jacobian because degree isn't well defined in higher dimensions. But what we can do, what we can do is consider the functor pick, and this. In good circumstances, this very somewhat explicitly is a set of line bundles after base change. But yes, so the functor pick kind of generalizes the Jacobian to higher dimensions or to higher dimensional varieties. And then once again, you can ask, and it's a group scheme in good circumstances, it's even in an abelian variety. So then once again, you can ask, can we find a Neron model for this? And the answer is hopefully yes, in nice circumstances. But and the way we find that is by working with pick and taking a quotient. So we're interested in pick because pick generalizes what we already know in the case of curves. Yes. So let's take a break here, and when we get back, we'll look at the Sertate.
Can I make another remark? Sure. So the good circumstances, this is more precisely, this is if and only if the valuation of the discriminant is 0.
That's right.
Yeah. Awesome. So it's quite good.
Yes.
You mean pick 0?
Yes, that's right.
What does?
So this is the pick 0 is the connected component of the identity. So I mean, pick is always a group scheme, and then so it has an identity, and then you can consider the connected component that contains the identity. But yes, that'll be discussed in the third topic in depth. All right, so let's take a break here.